Welcome to lecture for research methods. I'll be talking now about some stuff from chapter 11, I believe, going beyond the simple experiment. Remember, simple experiment, you have one independent variable, one dependent variable, and your one independent variable has only two levels, usually an experimental group and a control group. And you can see if some variable has an effect or not. And that's like obviously simple. The logic is clean, straightforward, and very useful for simple questions. Unfortunately, in our field, usually we don't ask very many simple questions. Most of our questions are more of the complicated nature. So we need to go beyond the simple experiment, and there's multiple ways to do that in terms of increasing variables and changing different variables and different combinations of variables. For now, we'll start by talking about what the simplest way of expanding, not adding any variables, but adding more levels of a variable. And obviously you don't add levels of a dependent variable because you're just measuring that. So we're talking about adding levels. We're talking about adding levels to the independent variable, right? So when we use more than two values of an independent variable, more than two levels, more than just experimental and control. So using 3 levels, 4 levels, however many more. But remember, in an experiment, at each level of the independent variable, you have usually some group of people, especially if it's a between subject design. So if you keep adding levels, you're adding more and more participants. So you are limited by realistic limitations, how many levels you can have. But theoretically, an infinite level of levels, right? So what does it do for us? So why would we want to use more than two values? Why we want to stray from simplicity? One reason, you can improve your external validity, right? And basically because you can generalize to a wider range of treatments, right? Because if you do a simple experiment, you basically have treatment versus no treatment. And so if you find there's an effect of treatment, you can generalize to that one type of treatment you looked at, right? But if you're interested, well, I want to know the effect of treatment, and I want to be able to talk about how this applies to, we're talking about therapy, cognitive behavioral therapy, Gestalt therapy, interpersonal therapy. I want to talk about different types of therapy. Well, if you want to do that, you don't want to muddy the waters by having just all different types of therapy and clumping them into one level of the independent variable. Okay, here's therapy, and all people get some type. No, we'll separate them out. So we'll have no therapy versus CBT versus Gestalt versus behavior therapy. Right? So here, the variable we're manipulating is type of therapy, and there are multiple levels. And if we do that, when we find, we measure our dependent variable, whatever it is, at the end, we can generalize our results about the effect of therapy to more than one type of treatment. Right? And we talk about treatment, we're talking about independent variable. Even when we're not talking about doing therapy. If you're doing listing different types of music and the effect it has on the speed you drive, right? Looking at different, country music, rap music, rock music versus no music. We can generalize the effect of music to more types of music, and we often talk about those being treatments, even though it's not therapy, right? So that's one reason to use more than two values of an independent variable. Another is it helps us identify functional relationships. And really it's the functional relationship between the independent variable and the dependent variable. Right? Because in a simple experiment, all you know is it had an effect, yes or no. But you don't know anything about the relationship other than its cause and effect. Well, what if you wanted to know, well, its cause and effect, is that cause and effect relationship true at all levels of the independent variable? Or if I continue to ratchet up the IV to more severe, longer, bigger, more of the independent variable, what happens to the dependent variable? Does it continue to grow as well, or continue to shrink, or does it change, right? So we're talking about looking at quantitative differences in the independent variable here, usually. And by doing that, we can then look at the relationship between the IV and the DV to get an idea if it seems to be linear or nonlinear, right? And linear just means that increases in the IV lead to predictable and incremental either increases or decreases, but always in the same direction, in the DV. So let's say we were looking at the effect of the volume of music on the speed you drive, right? So in a simple experiment, you do very low volume or no volume to very loud. Right? And you can say, oh, well, loud seems to have an effect. But what if you want to know, well, what is that effect? So you might look at very low volume. So think about our volume knob being on this dial that goes from 0 to 10. So one group of people gets it at a 1, another group gets it at a 3, another group gets it at a 5, another group gets it at a 7, another group gets it at a 9. Right? So we have different groups all at different levels of the independent variable. And we say, okay, well, at very low levels, people are driving slow. And the higher the level of the IV, the faster they drive. And if that's true, it's a linear relationship. May or may not be, right? You go do a study to find out. It may be that it increases, so you go from 1 to 3 to 5, people start driving faster. But once it gets kind of loud, maybe it levels off and they don't drive any faster, or maybe they start driving slower, like up at a 9, they're like, oh, it's so loud. They take their foot off the pedal, and it's this non-linear relationship. Right? If you'd done a simple experiment, you would never have known that. Right? So that's another reason to use more than two values, more than two levels of an independent variable, to get a look at that relationship and what happens if we increase or decrease the independent variable, right? Which is usually has some very real world implications, especially talking about treatment, because we don't want to just know if treatment works. We want to know how much treatment do you need, and the insurance companies usually want to know what's the minimum amount of treatment you need, right? What's the fewest sessions we can pay for, and you still show an effect with your clients. And so we need research to be able to find that. So when you're trying to identify, well, I've got to look at these different levels of my IV. How do I pick? Well, you scale your independent variable. And we're talking about scaling the IV. We're usually talking about doing some sort of pilot test, right? So before you do your big study, you want to go get some group of people. It could be just research participants, could be your friends, whatever. Usually it doesn't have to be too formal for pilot testing. And you're going to expose them to what you think are different levels of the independent variable, right? And for some things are easier to quantify than others. Like the volume thing, it's easy to go a 1, a 2, a 3, or 4 on the dial. Those seem to be, you have clearly different levels of loudness that correspond to the amount of power that's being sent to the radio, right? Other things, it may be less clear. Like, say, kind of a silly example, you're looking at the effect of smelliness of cheese on how appetizing it is, right? And how smelly cheese is fairly subjective. You probably can't go, okay, what is it? That's a 3, that's a 5. Okay, clear, I got 3 to 5 to 9, whatever. You may not be able to do that reliably. It may be true for you, but maybe other people perceive things differently. So you're going to go and you're going to pilot test, and you're going to make people smell a lot of cheese, right? And you're not going to have them rate how appetizing it is, right? That's your dependent variable, and you're not doing your study. You're doing something else. What you're doing is trying to figure out how much of the IV is there. So you have them smell the cheese, and you say, how smelly is this cheese? On a scale of 1 to 10, 1 to 100, whatever you want to do, and you have them rate the stimuli. Your representations of your independent variable, if it's a physical thing, if it's an experience, looking at a picture, sticking their hand in a bucket of water and telling you how cold it is, whatever. How much of it is there, do you think? And then you gather a bunch of data, and then from that data, you can then choose what stimuli, what experiences you're going to use in your study. And you're going to choose ones, first of all, that are consistently rated similarly across individuals, right? So if there's some piece of cheese that you use, and some people rate it at 1, some people rate it at 7, some people rate it at 3, they're all over the place, well, you don't want to use that in your study because it's not being consistently perceived the same way. And so you're going to have poor construct validity, for one thing, related to the construct of smelliness, right? You're not going to be really manipulating that effectively because you have no reliability in how it's being perceived. So you want things that are perceived all the same way. So identify those. And then you want to get some that are spread out, right? So if we have, again, kind of scale on 1 to 10 on smelliness, and you find, well, everybody rated this one a 1, everybody rated this one a 2, I'll use these 2. 1 and 2, that's good. 2 is twice as much as 1. Well, 2 is twice as much as 1, but it went from a scale of 1 to 10, and how different is 2 than 1? You may not have an effect. So if you're going to use 3 levels, if you have one that's a 1, one that's a 5, one that's a 10, perfect. Now we have them fairly evenly spaced out, equal distances between the points. And then we can look at, if there's some sort of linear or non-linear relationship. Okay. And this all, again, happens before you conduct your study. It's just doing pilot testing to pick the things you're going to, the stimuli, the experiences you're going to use to manipulate your independent variable. Right? Okay, and that's all in the name of identifying functional relationships. The thing I already alluded to a little bit is that using more than two levels of an IV allows for the improvement in construct validity. Right? We often talk about construct validity having to do with the dependent variable and measurement validity and all that stuff. But remember, it also applies to the construct of your independent variable. Right? So if I'm trying to manipulate smelliness, I'm going to do my best to do that. But and so the construct is smelliness. But what is smelliness, the construct, right? And how can I make sure that I'm manipulating that and not something else, right? There's always the possibility that there might be impurities in my manipulations, right? So if I get a bunch of different cheeses that have different levels of smelliness and I get people to rate them, and then I use them in my study, what if those different cheeses are not only different in their smelliness, they're also different in their texture or their color or the amount of cheese that's there, right? Now, I may not be so sure when I find differences in my DV. Are those attributable to the differences in the construct of smelliness, or are they other differences in the stimuli and the experiences that people are responding to? Right? And if you do a simple experiment, you just have two levels. It's hard to really identify that or tease that apart. But when you use more than two values of the independent variable, you can get at that by, again, looking at qualitative differences in the IV. Right? So if I have these cheeses, well, think of another example here. The effect of technology on receiving negative feedback. And if I do a simple experiment, I get somebody gets negative feedback either via technology or not via technology. Right? And people say, well, what if it has to do with the type of technology and not just all technology? Or people responding to different things. Well, if I really want to figure out what it is about my independent variable, what it is about technology that's causing people to respond differently, then I'm going to have face-to-face group. I'm going to have technology via maybe voicemail, via texting, via email, via chat over the internet. These different things to figure out what about that construct is driving some difference between this non-technology form of feedback, right? Or going back to the cheeses, like, okay, well, it's smelliness, but maybe there are different types of smells, like a sweet smell or a sour smell, right? So maybe I'm not just looking at quantitative differences in smelliness, like I talked about before, for that functional relationship, but maybe ones that are all rated equally smelly, but different types of smells. So non-smelly cheese to sweet smelling versus sour smelling to I don't know, whatever type of smelling there is. And then I can figure out what it is about that construct, and I get a better understanding of the construct that's having the effect, driving the effect. Lastly, it can be helpful for improving internal validity. And primarily addresses the problem of hypothesis guessing that you're faced with sometimes in simple experiments, right? Because simple experiment, if you have experimental group and control group, especially if you have an empty control group where they don't get anything, then people know I'm either in the experimental group or I'm not, and then you have kind of this demand characteristic, which may make them act in ways to try to support your hypothesis, right? Which clouds the picture. Okay, when I find difference, is it really because of my IV or because they guessed what condition they were in? And so it's a threat to internal validity, right? So we talk about this, these control groups, and if you have an empty control group, that's a problem because people who get nothing are clearly different than people who get something. More than just, so if we have smelly cheese versus no cheese, how much do you want to eat some cheese? Well, not only did one group get smelly cheese, they also got cheese to look at. And this other group who got no cheese, they got no cheese to look at, no cheese to smell, nothing in front of them to stimulate the idea of cheesiness. Right? So they're different in more than just that one construct. Which again clouds, well, why are these two groups different? Which is a threat to internal validity. Versus your placebo control group, where you try to have something where they get something, right? And then something is supposed to have no effect or be inert, right? Have no impact on the DV. The problem with placebo control group, you say, well, I can do a simple experiment. I'll just do a placebo control group. The problem with using those is sometimes you don't know what the effect of your placebo is. Like you assume it has no effect, but it might, and you can't know if nobody doesn't get something, right? You either get placebo or you get the treatment, especially for therapy, and really hard to define what a placebo group is for therapy, because what is an inactive treatment? And oftentimes it's been used in research. They say, well, they just get supportive therapy, where somebody will come in and they won't get this manualized treatment if they're not in the treatment group. They're in the placebo control. They'll just get to talk to some counselor. Okay, is that counselor really not being therapeutic? Probably not. I mean, they're a therapist. They probably are being therapeutic, so they are having an effect, right? Which you could argue, well, then you're finding out how much does this manualized treatment give above and beyond basic therapeutic skills and interacting with someone, getting some attention, which is an important question, but it doesn't tell you about the effect of getting this manualized treatment versus no treatment at all. Right? So the nice thing about, again, having more than two values of the IV is you can do both types of control groups, or you can have an empty control group, a placebo control group, and your treatment group. Then you can start to tease apart these different patterns of findings and determine, if the empty control group and the placebo control group are no different, then the placebo really did have no effect. And then you can just do this kind of straight comparison of your treatment to no treatment and talk about the effect of this treatment. Usually, though, the placebo does have an effect, right? But if you have an empty control group, you can at least then say, okay, the treatment was successful and it was better than no treatment at all. It was also better than placebo, but placebo was better than no treatment, right? And then you can talk about how much of an effect your treatment adds beyond placebo, right? And if it's not much, then, especially if placebo is cheap and your treatment's expensive, placebo is just as good, even if there's a statistically significant difference. If you're not moving people enough in terms of reduction of symptoms, going back to work, whatever it is, then your treatment may not be worthwhile. But again, having more than two values on IV allows for using both types of control groups, which increases your internal validity. Okay. In terms of analyzing the data, the approach here is to use an omnibus test rather than multiple pairwise comparisons, right? So start with just the simplest experiment that goes beyond a simple experiment, where we have just three levels of the IV, right? Group A, Group B, and Group C, right? And we're calculating how hungry they are for some type of cheese, right? And we're getting average scores for each group. Now, you could compare Group A to Group B, Group A to Group C, and Group B to Group C. And that would be all the comparisons, right? If you do that, you're doing multiple tests, and so you'd be multiple pairwise comparisons. The problem with that is, the more tests you do, the more likely it is that you're going to make at least one type of error. Right? So think about that. So anytime you do a test, there's some chance of making type 1 error. Right? If you set alpha at 0.05, you're capping the probability at 0.05. But if you do another test, now the probability of getting an error in that second test is independent of the probability of the first one. So it's all still 0.05, and the third one is still 0.05. But I would look at them all together. What are the odds that across these three, I'll get at least one error? It's more than just 0.05. Just like when you flip a coin. 50% chance heads, 50% tails. Flip a coin 3, 4, 5 times. On the fifth time, we'll flip a coin the fifth time. What are the odds it's heads or tails? 50-50, right? Independent probabilities. But if I tell you, if you flip a coin 5 times, what are the odds that it'll be heads at least once? At least once. Well, it's much greater than 50-50, right? Because here we're adding probabilities together, right? So the more tests we do, the more likely we are to make a type 1 error. So to get around that, whenever you have multiple comparisons you're interested in, you do something called an omnibus test, and that's not a type of test. It's just a big test, a test that tests everything at once. Like ANOVA is probably the most commonly used omnibus test, which allows for one test of all the effects at once. And so we'll see how could you test all the effects at once? Well, let me tell you. Well, you look at two things. The first thing you look at is within groups variability. Right? So we have Group A, Group B, Group C. If everybody in Group A scored exactly the same in how hungry they were for cheese, there would be no within groups variability for that group. Same thing for Group B, same thing for Group C. And how likely is that to happen? We say, well, hey, everybody in Group A got exactly the same level of the independent variable. They should be similar. Yeah, they should be similar, but they won't be exactly the same, right? Because people bring with them their individual differences and random responding and any kind of error added to it, right? And so there'll be differences in individual scores. Some of those differences are due to measurement error. Some of them are due to true error, where there are true individual differences. Right? And for within groups variability, we add the within groups variability of each group together. We just kind of sum all that up, and we call it error variance. And this term is maybe a little misleading because some of that variance, some of that variability of them not being exactly the same as each other, may be due to measurement error, but a lot of it is just due to individual variability, true, factual individual variability, where they really are different in how hungry they are for cheese, even though they saw the same thing, right? But we call it error variance nonetheless. I don't want you to be confused by that term. So we look at this within groups variability, we look at this error variance, and we also look at between groups variability. So now we look at this group, and if we want one number to represent this one group, everybody in Group A, what's the best number for that? Well, the typical number is the average number, is the mean number, the geometric mean. So add all the numbers up in that group, divide by how many we're in there, that's that group. Compare it to Group B's average, Group C's average, and we compare all those to the average of all three, right? So how much, and if we do that, we have, well, how much does Group A differ from the average of all three? How much does Group B differ from the average of all three? How much from Group C? See what I mean? So if they're all the same average, if A, B, and C are all 10, then the average of all three would be 10, and none of them would deviate at all from the grand total mean, and you would have no between groups variability. And that means that your independent variable had no effect. Now, these groups might differ some, right? And they might differ some because of that within groups variability. And real quick, let me see. The between groups variability we call treatment variance, is the other term for it, because it's when groups differ, we assume it's because of treatment effects, right? But some of that between groups variability will be due to within groups variability, error variance. So what we do is we basically parcel that out and then look at a ratio of which is the F ratio, which is you calculate for ANOVA, which is conceptually the ratio of between groups variability to within groups variability, right? So if the between groups variability is made up entirely of within groups variability, like the only reason that these three groups differ is because of individual differences within the groups, then the ratio of between groups to within groups would be 1. Right? As the groups differ from each other more than can be explained by that within groups variability, then the numerator of that fraction of that ratio between groups variability, the treatment variance, gets bigger. And when it gets bigger and that bottom stays the same, the ratio gets bigger and the F ratio gets larger than 1. And the larger it gets than 1, the more likely it is to be statistically significant, right? So if there's no effect of our treatment, we expect the ratio to be equal to 1. We expect the F to be 1, right? And it's usually not, even if there's no effect, it's not 1, but it's usually pretty close to 1, right? It may even be oddly enough less than 1, which is a weird mathematical thing. But again, as it gets bigger than 1, we start saying, oh, maybe this is an effect. And then you can have SPSS tell you, look up at a chart, well, how big of an F ratio do I need to say that it's statistically significant, that something about these three means is different. And if you look at a chart, you'll look up with the degrees of freedom, which depends on the number of groups, the number of participants in each group. But kind of a general rule to kind of keep in the back of your head, whenever your F value excuse me, is above 4.16, thereabouts, it's more likely to be significant if you have 25 people or so per group and no more than in 4 groups. Again, the more groups you have and the fewer people you have, the bigger the F ratio has to be significant. So once you get that F ratio, what does it mean? Well, it means your treatment had an effect. And if we have 3 levels, You could look at the means and say, okay, well, this one looks bigger than this looks bigger than this, and I can interpret this, right? Sort of. The significant F ratio doesn't mean that, if you have A, B, and C, and the means are 9, 6, and 4, right? Doesn't mean that 9 is necessarily bigger than 6, or that 6 is different than 4. Probably 9 is different than 4, but not even that necessarily. All it tells you is that something is different between these groups. Right? But to look at whether or not one group differs from one other group in a statistically significant manner, you have to do something called post hoc tests. Right? So here's where you come in with a Tukey test, a Chaffee, a Bonferroni, whatever, and you do those pairwise comparisons we talked about at the beginning that you can't do. Right? And now you can do it if you had a significant F. If your F ratio is not significant, then you don't get to do the post hoc tests. And that's what protects you from that inflated error rate, because we've already done one test to say there is an effect here. I'm confident there's an effect here. Now we just got to figure out what it is, rather than kind of sorting through the details, looking for little effects where you might randomly happen to find something that's not really true. So we've done the big test. Something's here. Now we just got to find out what it is. So you do these post hoc tests. And you're basically doing pairwise comparisons, or you might do post hoc trend analysis, less commonly, which is another way of doing post hoc tests, kind of in a correlational sense rather than mean comparisons. And then you can make sense of your data. And it might be that, if you have that 9, 6, and 4, that 9 was bigger than 4. But that's the only significant pairwise comparison. That 9 and 6 were not statistically significant different, and 6 and 4 were not statistically significant different. Right? In that case, then Group A was people who smelled the Group A cheese were significantly more hungry than people who smelled the Group C cheese, but no different in terms of their hunger than the Group B. Right? And people in Group B were no different than people who were in Group C. Could be. Or it could be that 9 is different than 6, and 6 is different than 4, and 9 is different than 4. And then you have all groups different from each other. It just depends on the numbers. Okay, that's all for now. Take care. Welcome to the lecture for research methods. I'll be talking some more about expanding experimental designs beyond a simple experiment. Right. So before we talked about going beyond just 2 levels of independent variable to multiple levels of the IV. Now going even further than that, saying, well, what if we add another independent variable, or more than 2 independent variables? Whenever we do that, we're talking about factorial designs. Right? So first, let's just talk about some of the terminology involved with factorial designs, factorial experiments. A factor, in this context, is an independent variable. Right? If you're talking about factor analysis, that's a whole separate pot of beans. Right? Then you're talking about something that's a coherent construct that's identified by looking at multiple pieces of data. That's something else. Here, factor is the same thing as independent variable. So a 2-factor experiment has 2 independent variables. A 4-factor experiment has 4 independent variables, right? And that's all that the factor means, right? In terms of how you write about factorial designs, often you see this kind of nomenclature where you have some number, x, and some other number, maybe another x and another number, and so you read the x as by. So a 2x2 design, a 2x2x3 design, and the numbers will always be at least 2. You'll never see a 1 by something, right? Because the number itself represents the number of levels of an independent variable. Right? An independent variable has to have at least 2 levels, right? We're talking about therapy versus no therapy. You can't just look at therapy. You have to look at versus something else, right? So the numbers will always be at least 2, right? And if you have a 3, that's 3 levels. So you could be looking at no therapy versus therapy no therapy versus CBT versus client-centered therapy, right? Be a 3, 1 factor, 1 independent variable with 3 levels. Now, so each number tells you the number of levels of an independent variable. How many numbers there are tell you how many independent variables, how many factors there are, right? So, because each number corresponds to an independent variable. So a 2x2x2 design, that's 3 2s, has 3 independent variables. A 2x2x3 still has 3 independent variables. It's still 3 numbers. Just one of them happens to have 3 levels, and the other 2 have 2 levels. Right? Okay, when we talk about factorial experiments, it's easiest to talk about the simplest iteration, which would be a 2x2 design, right? Because we have two independent variables and both have just two levels. They could have more, they can't have less, and you have to have at least two independent variables to be factorial. So this is the simplest version of a factorial experiment. In this example, looking at independent variable of therapy modality, so therapy being delivered either face-to-face or online, and the other variable looking at the presenting problem the clients are presenting with. And the dependent variable is symptom severity post-treatment. Right? Now, therapy modality is a true independent variable, at least it potentially is. And if you do the study right, it should be, where you assign people randomly to one or the other of the levels of the independent variable. Right? They don't get to choose that they want face-to-face or online. If they get to choose, then you got this confound. And, well, maybe people who choose face-to-face are actually going to do better. People who choose online are going to do better, whatever it is. We don't let them choose. We randomly assign to take away that difference between groups. So if we're randomly assigned to create approximately equal groups, so such that people face-to-face, people online should be not that different from each other because they've been randomly assigned to one of the two groups. Presenting problem, can't do that. Right? You can't assign somebody to have social phobia or to have specific phobia. They have it or they don't. Right? So this is presenting problem is not a true independent variable. It's a quasi-independent variable. And a lot of factorial designs you'll see include at least one quasi-independent variable. Or you'll have one true independent variable and then another one that's quasi-independent. Usually something about the some participant characteristic. Gender is a very common one that you see. And that's perfectly fine and appropriate. Not necessary for factorial design. Factorial designs don't necessarily include a true independent variable and a quasi-independent, but they can. And when they do, the only thing you have to be careful about is how you talk about that quasi-independent variable. So we can't talk about the effect of presenting problem because we're not assigning people to have one or the other. And because we're not assigning them, we can't use the word effect. We can only talk about cause-effect relationships if we have that random assignment. It's a prerequisite. Right? Then why are we looking at it? We can't talk about effect. Well, we can still talk about differences. Right? The difference in outcome for people with social phobia as compared to people with specific phobia. We can use the word difference, we just can't use the word effect. It's restricted to when you meet all the prerequisites for an experimental design. Right? So in this one, you see some make-believe data here. Imagine symptom severities occurs on a scale of 1 to 10. So we see, okay, face-to-face, you got some people not doing that well with social phobia. Hey, and online they look pretty good. Looking at specific phobia, well, face-to-face they didn't do that well. Online they did pretty good. Well, how do we make sense of all these numbers? We've got these 4 different numbers and different combinations of pairings with factorial design. Well, you look at a couple things. One thing we know is that there are 4 simple main effects, and you can look at these, but it's not the first thing you interpret. Right? It's the first thing that catches your eye, so we'll go ahead and talk about it. And a simple main effect is when you just are looking at one of the variables. So therapy modality, face-to-face versus online. What was that like at one level of the other independent variable? So face-to-face versus online for social phobia. 8 compared to 2. Right? So 8 minus 2 is 6. So there's a difference there. And that probably is statistically significant difference, right? So looks like there's a simple main effect there. So that for people with social phobia, face-to-face was not as effective as online therapy, right? So there's one main effect. Look directly below that, we got specific phobia, 2 versus 7, a difference of 5. So for specific phobia, looks like face-to-face was better than online. Right? So there's 2 main effects. Now if we look vertically, right, comparing 8 to 2, 8 minus 2, 6, looks like for face-to-face, social phobia is better than specific phobia. There's a simple main effect. And then again here, looking vertically, 2 versus 7, difference of 5. For online, so at this one level of therapy modality, social phobia was better than specific phobia. Right? So those things catch your eye, but that's not the first thing you interpret. The first thing you interpret usually are the main effects. So the main effects, which if you have a 2x2 factorial design, you have 2 main effects. Right? And the easy way to think, well, how many main effects am I going to have? How many variables you got? For every independent variable you have, you're going to have a main effect. So 2x2 design, 2 main effects. 2x2 by 3, 3 main effects. 2 by 4 by 2 by 2, 4 main effects. Right? So to get the look at the main effects, you look at the marginal means. So we got the marginal means already in here. That's just the means you could calculate in the margins of your little graph. Your 8 plus 2 is 10 divided by 2 is 5. So the marginal mean there is 5. 2 plus 7 is 9 divided by 2 is 4.5. And then I can compare those two. 5 minus 4.5 is 0.5. Not that different. Right? So what are those numbers? What are those main effects? Right? So whenever I average 8 plus 2 divided by 2, I'm averaging across therapy modality. So basically I'm saying, what was the outcome like for people with social phobia? Regardless of what type of therapy they received. So I just want to know, in general, hey, how'd the folks with social phobia do? And the answer is, hey, they did all right. 5. Well, they do better, they do worse. People with specific phobia, about the same, right? They did 4.5. So that's the main effect of presenting problem. Again, I said we don't talk about effect for quasi-independent variables. Here's an exception. We talk about main effects. There's no other word. It's not a main difference. Right? It's called a main effect. So the main effect of presenting problem, probably not one. Doesn't seem to be a difference in outcome for people with social phobia versus specific phobia. And then we look at face-to-face versus online for this data set. We get the same thing. 8 plus 2 is 10, divided by 2 is 5. 2 and 7 is 9, divided by 2 is 4.5. Compare them, difference of 0.5. So again, comparing face-to-face versus online, regardless of, averaged across presenting problem. So it's kind of regardless of the other variable or averaged across levels of the other variable. What is the effect? So what's the big effect of therapy modality? No real effect. Face-to-face wasn't that much better than online. Online wasn't that much better than face-to-face. They probably essentially equal, not statistically significantly different. Right. And that's what a main effect tells you. It tells you the effect of one variable averaged across levels of the other variable. Right. In this case, the main effect's kind of misleading, right? Because if you said, oh, well, was the face-to-face online, were they different? If you look at this 5 and 4.5, you go, no, they look about the same. Were they the same? No, they weren't. Look at this, the simple main effects. 8 versus 2, that's different. 2 versus 7, those are different. There was a difference in modality, but that difference depended on the presenting problem. And that's where you get really the interesting part of factorial designs, the interaction term. Right? So you'll get however many main effects you have variables, and then you'll have as many interactions, basically the number of variables you have minus 1. So when we have 2 variables, 2-factor experiment, we have just 1 interaction. If we have 3, you've got at least 2 interactions, because then you have a 3-way interaction term, which gets a little more complicated. We won't worry about that right now. Looking at just a straightforward 2-factor design with an interaction. An interaction says that the effect of one variable differs, so the effect of one variable on the DV differs across levels of the other variable, other independent variable, usually, right? So, and there's 2 ways to interpret it. You can looking at your chart, you can go vertically, you can go horizontally. In this case, it makes the most sense to talk about the effect of modality, because you can't really talk about the effect of presenting problem. We'll talk about the difference. So here we say, okay, face-to-face versus online. And we say, there we go. Face-to-face led to a worse outcome than online for social phobia. Right? 8 was greater than 2. However, and however is tell you, oh, I got an action here. However, face-to-face led to a better outcome, lower symptom severity, for specific phobia than online. Right? And that's probably the most straightforward way to interpret this interaction. You can also always interpret it vertically. In this case, it doesn't make as much sense, but you could say for face-to-face therapy, people with social phobia did more poorly than people with specific phobia, whereas when therapy was delivered online, people did better when they had social phobia than when they had specific phobia. So whenever you interpret an interaction, the main thing is to mention all 4 cells, or all the cells you have. If it's 2 by 2, it's all 4 cells, right? So basically you're going to say, the effect of this variable was this here. However, it was different this other way. And you talk about all the cells. And sometimes it can be, the effect is, A is, going back to our other one, 8 is greater than 2, but 2 is less than 7. That's the easiest kind of interaction to interpret. But sometimes it's a little more complicated, where you have maybe 8 and 2, and the other one is 4 and 3. Right? So 8 is bigger than 2, and 4 is bigger than 3, but 8's much bigger than 2, then 4 is bigger than 3. So still the effect is different. The effect is bigger at one level than at the other. Okay? And that's also an interaction. Which will be more clear probably when we talk about graphs here in a minute. Okay, so again, a factorial design, helpful in a lot of ways. In many ways, you're combining multiple simple experiments, right? If you have, I wonder what the effect of this variable is. I wonder what the effect of this variable is. Hey, look at them both at once. And if you just say, what's the effect of this variable and what's the effect of this variable, looking at the two main effects, you're doing two simple experiments in one shot, right, with one study. And that's good, you're adding information. But what's really kind of interesting about these factorial designs are the interaction terms, because then you look at how do these variables interact? How does the effect of one variable differ, or does it differ, at different levels of the other variable? So in terms of uses of the interaction term and what it's good for, one thing would be increasing external validity. And here, kind of ironically maybe, you're looking for non-significant interaction terms. Right? So if you have some treatment that you think is effective, right? And people say, oh, well, it's effective for this group, but what about this group? What about this group? Well, maybe it only works for people of this ethnicity or of this age or who speak this language. Right? So what you do is you have one variable being treatment, so yes treatment, no treatment, and then another variable you put in there that's culture or age or ethnicity or language spoken, whatever. Right? And you're usually not that interested in the main effect of gender, age, or whatever, but you're interested in that interaction. You want to know, okay, the treatment, maybe there's a main effect for treatment, yay, but was that main effect true across all levels of ethnicity? Right? If so, then there's no interaction. If it's not, if it's true for one group but not for another, well, now that's a significant interaction, and your effect doesn't generalize to all groups, right? Which is important to know. But again, usually you hope that you have non-significant interactions when looking for promoting external validity of a theory of treatment. Anyway, another use is ruling out alternative explanations. Say, oh well, maybe you found what you found because of demand characteristics. Maybe because there's experimenter effect. Maybe because it uses it's just one type of stimulus you used. It wouldn't work somewhere else. So whatever people think the other explanation is, you put that in as a variable. And you look for an interaction to say, okay, does my true independent variable have an effect regardless of who the experimenter was, regardless of what kind of instructions the subjects were given, regardless of what the type of stimulus they got. As long as they got the therapy, it didn't matter if it was an experienced therapist, a young therapist, whatever. Right? So the more ruling out that, okay, no, I didn't find this effect just because of this. I can show you it happens at all levels of these other variables that you think are causing the finding I found elsewhere. Right? Also helpful for showing exceptions to some rule. So maybe somebody has published something saying, okay, this treatment works for this, or this experience has this effect on people. And you look at that and you read and you go, yeah, maybe, but I know some people that it wouldn't happen that way with. People that had an abuse experience. People that are addicted to substances. People who come from single-parent families will be different than people who come from dual-parent families on this with this effect, right? So if you think, well, I think it's true, but not with somebody else, you do the study, and what you end up doing is you look for an interaction to say that, okay, yeah, I'm basically going to replicate this other person's finding as one of my simple main effects. Okay, here's your effect, and it's true for this group, but hey, look, it's not true for this group because that variable interacts with this other variable. And it could be ethnicity, age, experiences, whatever. Right? So often helpful to kind of expand our knowledge. Once we think we know something, we go, okay, who is that true for? When is it true? And that's what interactions can tell you, is that, well, it's true, but only when this other thing is true. So A is greater than B only when C is greater than D. Make sense? Last thing helpful sometimes in identifying essential elements, especially for therapy, you may find that, okay, we think this characteristic is, therapist experience is a good thing. We think therapist warmth is a good thing. And does it matter if you have both, right? And if you have an interaction, you might find that it does matter, where you have main effects of both, where more experienced therapists, better outcomes, therapists with better warmth, better outcomes. But if you have both, if you're an experienced and warm therapist, that the outcomes are far and above any other group. And then we've got an interesting interaction, and we realize, okay, well, then this is the best combination of these variables. Right? For me, understanding interactions and trying to interpret them is usually easiest in terms of looking at graphs. So, got some here. Looking at the effect of type of music and traffic density on speed at which somebody drives. Okay, kind of a silly thing, but so you see, you got here when you graph it. You're always going to have one of your independent variables down at the bottom. So traffic density, sparse or heavy, right? 2 levels. And then I've got your other independent variable will be in a key or a legend. So I've got heavy metal is the little oval, and classical are the triangles. Right. So look at the first graph, and we got, okay, when traffic is sparse, people drove faster listening to classical music than heavy metal music. When traffic was heavy, people drove faster listening to classical music than heavy metal. Right? So this line is above this line. This line is classical. So basically, this graph is telling me pretty clearly that people drive faster when listening to classical music than when listening to heavy metal music, regardless of the density of traffic. Right. So the effect of music was the same, regardless of the level of the other variable. So no interaction there. Right. So there's a main effect of type of music. Right. And then to figure out did density of traffic, is there a main effect of that? And what you have to do is imagine drawing a line between the oval on the left and the triangle and finding the midpoint, putting a little X there. And the same thing for the other triangle and the other oval. And basically what that does is says, okay, averaged across heavy and classical, the midpoint between those two ends of that line is the average for sparse. And then I'll do the same thing with heavy. And if those 2 points are even with each other on a horizontal plane, there's no vertical distance between them, then there's no main effect. In this one, there's no main effect of heavy or sparse. Now, move over to the next graph, a little more interesting, right? So here, we've got, it's a little off kilter, but when traffic was sparse, people drove faster listening to classical than when listening to heavy metal. However, when traffic was heavy, they drove faster listening to heavy metal than when listening to classical. So here, the effect of music is different depending on the density of traffic. And then trying to look at the main effects. Again, you've got to find the midpoints between the triangle and the oval, and the triangle and the oval. Line them up. Looks like there's not a main effect of traffic density. And then now the main effect of heavy metal versus classical, the main effect of music type, harder to see when they're crossed over like this. But what you do for this one is you find the midpoint of the line that connects, the midpoint of the line that connects the triangles and the midpoint of the line that connects the circles. And if those things have vertical distance between them, there's a main effect. If not, no main effect. And this one, when they're fully crossed like this and you get this X, there's no main effect of either variable, and it's all interaction. Okay. And in the third one we have here, when traffic was sparse, people drove slightly faster when listening to heavy metal than classical. Probably not significant, they're pretty close together. But when traffic was heavy, they drove much faster listening to heavy metal than classical. Right? So we see that we have an interaction. There's different effect. Right? The difference between heavy metal and classical, not much when sparse, but a huge difference when heavy. So the effect of music type is different at different levels of traffic density. So clearly an interaction there. And again, anytime they cross or even they look like they're going to cross, if they're not parallel, it's an interaction. If they're parallel, no interaction. So that's the easiest thing to look at in one of these graphs. Main effects, looks like overall heavy metal is greater than classical. And that probably would be significant. The middle of that line is higher than the middle of that line. But that main effect is being driven by the fact that at heavy traffic, heavy metal is way faster. Because that main effect isn't really true for sparse. There's probably not a simple main effect there. Right? So that main effect is qualified by the interaction. The main effect isn't always true, even though it may show up statistically as a significant main effect. We know, even looking at the graph, well, there is a main effect, but it's only part of the story. The interaction is the bigger part of the story. And then if we look at sparse versus heavy, you find the midpoint there and the midpoint there. Looks like heavy is probably higher. People drove faster in heavy traffic than sparse traffic. But again, even if you have a main effect that shows up, looking at the graphic, it's not really true, right? Because actually, when looking at the classical, people drove slightly faster, probably not a significant difference, but slightly faster in sparse. Right? So the main effect isn't true for all levels, but statistically it may show up because the simple main effect of the heavy metal is so big. Okay. In terms of interpreting the results, looking at the statistics, you'll get an F for the overall model. We don't usually worry about that. What we're interested in are the main effects. Right. And again, you have as many main effects as you have independent variables. And you'll get an F ratio for each main effect. Right. So it's not like, do I have significant main effects or not? So was this main effect significant? Yes or no. Was this main effect significant? Yes or no. Right. Each one is separate. You can have one be significant and the other not. And they're not dependent on each other. Right. So you have an F ratio in ANOVA, just like you always see. If you just have two levels of independent variable, two levels of a factor, easy to interpret. If the F is significant and you have two levels, whichever one numerically is bigger than the other is more, right? And they are statistically significantly different. If you have more than two levels of an IV, more than two levels of a factor, so let's say our our music type, we had a classical, heavy metal, and rap, and we have a significant main effect of music type. All we know is the type of music people listen to had an effect on how fast they're driving. We don't know which one's bigger than the other. We can look at the numbers and say, well, this one looks bigger. But if you have one's a 9, the other's 8.5, and the other's a 4, is 9 bigger than 8.5? Technically, yes, but is it statistically significantly different? Don't know. So if you've got more than two levels in IV, it's just like we talked about before. When you have one IV with multiple levels, you got to do post hoc tests to identify which means differ significantly from each other. And the other thing to think about when looking at main effects is there an interaction? Is the main effect qualified by the interaction? And interactions typically qualify main effects. Not always. Sometimes there's a main effect and it's true at both levels of another independent variable. It's just the main effect is bigger at one level than the other. Sometimes it's true at one level, not true at the other. Or sometimes it's opposite at one level than in the other. In those cases, definitely qualified. And you don't want to overinterpret main effects. So typically you say, there was a main effect of blah, blah, blah. However, this was qualified by a significant interaction. And then you want to interpret the interaction. You don't waste too much time talking about the main effect. For interaction, again, you get one F ratio for that interaction. And again, all it tells you is, there's an interaction. It doesn't tell you which means are significantly different from which one. So if you got a 2 by 2, you got 4 means. And you got a lot of comparisons to make. So again, you're going to do post hoc tests. And SPSS will do that for you, thankfully. But you could also always do it by hand and then interpret the pattern. And when you interpret the pattern, always make sure you talk about all the cells. Okay. And that's the key to successfully interpreting interaction. Okay, that's all for now. Take care.